Hello, today we'll be talking about black holes. My fellow classmates and I decided to contact a few experts to help us on our deep dive into black holes. I am proud to say that the 2017 Nobel Prize winner D. Rainer Weiss responded to the questions we asked. The first question was, how would you personally describe a black hole? Dr. Weiss replied, the two key facts are there is, at some distance from the center of the black hole, a point of no escape, the event horizon, where nothing has enough energy to leave the black hole. At the edge of the event horizon, Stephen Hawking discovered that the quantum theory would cause a vacuum of space to make virtual particle pairs in which one element falls into the hole while others escapes. It is an effect that may be noticeable in small mass black holes. The other thing one can be sure of is that the classification gravitational, like Einstein's general relativity, blows up. At some deep point in the black hole where mathematics becomes singular, most physicists believe that a proper quantum theory of gravity would no longer have such a singularity. Now let's compare that to our group knowledge, starting with the innermost layer of a black hole, the singularity, a point at which time and space cease to exist. A singularity does not abide by the laws of physics. Also, keep in mind, as we move away from the singularity, the gravitational pull decreases. Past the singularity is the event horizon, the Schwarzschild-radius. This is a point of no return. Only here can an object escape from a black hole by having access to be as fast as speed of light. Now, as we know, light doesn't have mass, which allows for an unstable orbit about 1.6 Schwarzschild-radii past the event horizon. This is called the photon sphere, where photons can continually spiral into a singularity or back out into space. Next comes the accretion disk, which is made of gas and dust. These particles are moving about a quarter of the speed of light. Looking into a black hole on its side makes the accretion disk look like it orbits around the black hole, but in fact, it's the light from the accretion disk that's being bent around. So we see the bottom be bent from the bottom around to the top, as well as these photons radiate out of the black hole. This is called Hawking radiation, and as this Hawking radiation carries out energy from the black hole becomes smaller, and at some point it completely disappears.
For this project, we approached a few experts with a couple questions relating to our project, and we were very lucky to hear back from 2017 Nobel Prize winner Rainer Weiss. Dr. Weiss received his Nobel Prize for his laser interferometric technique, making him more than qualified to answer a few of these questions. When we asked him, if a star collapses into a black hole, what happens to the rest of the star's mass that doesn't go into the singularity when a supernova occurs? He replied, when a star collapses to a black hole, depending on the angular momentum of the star and whether it has an accretion disk of mass around it, much of the mass of the star that is destined to fall outside of the event horizon is thrown into the surrounding space. Even not all the gravitational radiation emitted by matter that is being accelerated by the collapse winds up being eaten by the black hole. The details of exactly how much mass is taken up by the black hole requires real modeling of the matter high moving field gravity given by the solutions of general relativity, not an easy calculation. What can we learn from this? While all black holes have the same process of formation, every black hole's amount of matter to fall under the event horizon and into this singularity is different, depending on the mass of the possible accretion disk and angular momentum of the collapsing star. All mass that doesn't inevitably fall underneath the event horizon will be thrown out into space and go out and possibly form new stars and galaxies. Meanwhile, all the matter that falls under the event horizon will fall into the singularity and will be warped around space-time. The textbook describes the event horizon as the region that separates the things trapped inside it from the rest of the universe. I'd like to imagine that as an instant space quicksand. As soon as you cross it, there is no going back. You will get sucked in. The event horizon can't be calculated using only the mass of the star. This formula is called the Schwarzschild-radius and is written RS equals 2 the gravitational constant times mass divided by c, which is the speed of light, to the second power. Mass is the only changing factor in this formula, and what we have found that it is the larger the star's mass, the larger the Schwarzschild-radius.
Now that we understand the life and death of a black hole, and the properties and definition of a non-rotating black hole, we can discuss rotating black holes. As everything in the universe must obey the law of conservation of momentum, we can theorize that as a star core collapses to a single point and its radius therefore shrinks, its rate of rotation must increase. This rotating black hole has some new properties. First, the ergosphere. It is a shell that extends from the poles of the black hole, affecting a region around the black hole outside the event horizon. This shell becomes flattened as the rate of rotation of a black hole is larger or smaller. Space within this shell experiences an effect known as frame dragging, which is that space-time itself is being dragged along by the rotation of the black hole. No body in the universe can remain still in that black hole, as the energy required to remain still would need to exceed the speed of light. Because of this, there is a theory that energy can be extracted from a black hole known as the Penrose process, theorized by Roger Penrose in 1971. This states that if a spaceship was to enter the ergosphere of a black hole and eject a certain amount of mass into the black hole, that spaceship could then leave the black hole with more energy than it entered with. The energy would be extracted from the rotational energy of the black hole, and over time the black hole would lose rotational energy to this process. Now that we know more about rotating black holes, we have to come to terms with some of the problems that plague rotating black holes. The first problem is one of the larger ones. What is spinning about a rotating black hole? We've discussed that the ergosphere is containing rotating space-time in it, but the black hole itself can't be rotating. Space-time is a region of space. The ergosphere is a region of space, and the singularity is a single point. A point cannot contain any rotational properties. The next problem, or part of, is ISCO, the innermost stable circular orbit. The innermost stable circular orbit is the closest orbit a body can hold to another body without falling into that body. An example would be, for the Earth, if we were to move the moon within the ISCO, the moon would be doomed to fall into the Earth. For a black hole, the ISCO is the innermost edge of the accretion disk, as anything inside that is doomed to fall into the black hole, no matter how fast it's going. This is important to us because of its effect to the rotation of the main body. ISCO is entirely dependent on the rotational velocity of a body. As the rotational velocity of a body increases, the ISCO, radius of the ISCO from it to the center of the body, decreases. As such, as a black hole spins faster and faster, its ISCO gets closer and closer to the event horizon. Because of this, and because of the speeds black holes rotate at, the rotational speed of a black hole is measured on a scale of 0 to 1, with 1 being the speed of light. If a black hole is rotating at, in this case, a 1, the ISCO of that black hole is on the event horizon. This poses one of the larger problems in our current understanding of the universe, a naked singularity. This is to say that if the ISCO is inside the black hole, and the black hole's rotational velocity is greater than 1 on our scale, light will be able to orbit within the black hole and potentially escape. Thus, the singularity is exposed to the universe. Our understanding of mass and physics breaks down when the black hole's rotation is measured greater than 1 on our scale. What can we conclude from this understanding? There are two main conclusions that we can come to. Either our understanding of physics is wrong, and it is not a true singularity, or space-time is not truly rotating, or our understanding of black holes is wrong. Either way, both pose as one of the larger questions of the 21st century, and hopefully will be solved by the understanding of quantum gravity. Thank you.